Welcome to section 1.6. In this section, we will be dealing with first-order linear differential equations. So recall from our introductory sections, a first-order differential equation is one whose highest derivative taken is a first derivative, and a linear differential equation is one that produces no powers greater than 1 on any of the derivative functions. So a first-order linear differential equation is one that can be written in the following form, that is y prime plus p of x times y equals q of x. So if it can be written in this form with p and q being continuous functions on a given interval, then we consider this differential equation first-order linear, and we have a method to be able to solve this type of differential equation. And we are, in this section, going to derive that process and then see how we use it across some different examples. So every first-order linear differential equation can be solved by multiplying both sides of this equation by a function I of x, which is known as the integrating factor. So our job now is to find what I of x is. So what we want, are the end result that we're looking for, is we want the left-hand side of this equation, when multiplied by I of x, to become this expression, I of x times y quantity prime. So we want it to be the derivative of I times y, essentially. So for now, we want, when you multiply the left-hand side, so this is the left-hand side of that differential equation, when we multiply it by I of x, this is what we're looking for. We're trying to make it equal to that expression, I of x times y quantity prime. Now, if we multiply the right-hand side of that initial equation by I of x as well, then that gives us this new equation. So that gives us I of x times y prime equals I of x times q of x. That was the right-hand side up here was q of x, so times I. So this is our desired equation. If we integrate both sides of this, the left-hand side, the derivative and the integral would undo each other. And that's kind of the point, is that's what we want to happen. So we would get I of x times y equals the integral of I of x times q of x dx. And then to solve for y, we would divide by I of x. So we would get our function y of x would be 1 over I of x times the integral of I times q dx. Now, we need to figure out what I of x is. So we need to figure out what I is. So we're going to expand our earlier desired equation. So this one right here, expand this out. So distribute the I of x on the left-hand side and then actually take this derivative of the right-hand side using like the product rule. So if we distribute, we get I of x times y prime plus I of x times p of x times y equals, on the right-hand side, we use the product rule. We have a function of x times a function of x. So that's going to be I prime of x times y plus I of x times y prime. We do have a term in common here. That's I times y prime. We can subtract that off of both sides. So we have I of x times p of x times y equals I prime of x times y. And a common factor of y here, assuming that y is non-zero. Divide that away. So we get I of x times p of x equals I prime of x. Now, this equation, this differential equation that we just got right here, that is actually separable. So that's the type of differential equation we talked about in the previous section. So if we set this up, we get I of x times p of x equals, so this would be like di dx. If we set that up using the Leibniz notation, split this up. So we're going to get p of x dx on the left-hand side, divide this I under here. So that's 1 over I di. Then we can go ahead and integrate both sides. So we get integral of p of x dx. We don't know what p is. For I, though, if we have 1 over I, we can take the antiderivative. That's the natural log of the absolute value of I. So let me go ahead and switch these around because we're solving for I here. Then to get rid of the ln, we need to raise both sides into the exponent of an e. So we're going to get absolute value of I equals e to the integral of p of x dx. Now, when it comes to solving for kind of the final form of this, we're going to be able to get rid of the absolute value, and we're not going to have to include a plus or minus. We're also not going to have to include a constant of integration here. So the reason for this is this integral would produce a constant of integration, right? It would produce a plus c up here. That result would become, e to the c, and that would get put in front as a different arbitrary constant. That arbitrary constant would absorb the plus or minus from the absolute value. But the nice thing is, because this constant is arbitrary, it really doesn't matter what its value is. So for the simplicity of the formula, we're able to make it whatever we want. So this is an important thing to take note of here. So since the constant, actually, let me get rid of that plus c there. Since the constant of integration is arbitrary, we can choose its value. So we could choose it to be anything, but of course we want to choose it to be as simple a value as possible. So we're going to choose its value to just be 1. And I'm not talking plus 1 up here. I'm talking about when it comes down to the front, we get the c out in the front of the expression. That would be a 1. So in essence, it doesn't show up, and that's kind of the point. So I of x, this integration factor, is e to the integral of p of x dx. And that value for the integrating factor is what gives us the key to solving these first-order linear differential equations. So once we have that, we're going to be able to multiply that into our formulas. So we're going to be able to set up this version of the equation and solve that using integration, okay, as if it is kind of like separable, except we're not going to have to separate it. We already have the prime over here. So we're going to be able to then solve this directly without any further kind of hiccups, if you will. So here we have top of the next page. To solve the linear differential equation in this form, multiply both sides by the integrating factor and integrate both sides. So let's go ahead and try an example of this. So solve y prime plus 2xy equals 2x cubed. So we have p of x is the term in front of the y, so that's 2x. Q of x is the function on the other side, so that's 2x cubed. We need the integrating factor, I of x, so that's e to the integral of 2x dx. Antiderivative of 2x is x squared, so we get e to the x squared. And again, we don't need that arbitrary constant in this expression. So from here, we can set up that desired equation, that left and right hand side. So we get I times y, so that's e to the x squared times y prime. Equals I times q. So e to the x squared times x cubed. Excuse me, 2x cubed. From here now, we can integrate both sides. The left-hand side, because it's the integral of a derivative, they just undo each other. So we have y e to the x squared equals integral of 2x cubed e to the x squared dx. So in the process of solving this, we need to do a couple of things here. So we can set up a substitution for this. Normally I would call it a u sub and let u be the variable, but we're going to use u again in just a minute. So I'm going to go ahead and call it t. So we're going to let t be the x squared that's up here. Then dt is going to be 2x dx. Now, when we set it up this way, so we got y e to the x squared equals integral. This is an x cubed, but 2x of it gets covered by the dt. This x squared gets covered by t, and there's still an x squared left in here to get covered by t. So this becomes t e to the t dt by doing that substitution. Now, this is something that we can solve using another technique of integration, and that is integration by parts. And this is why I wanted to hold on to u a little while longer, because we can take u and v. So we're going to get, so u is just going to be t, dv will be e to the t dt. So du is dt, v is just e to the t. From there we get, so it's u times v minus the integral of v du. That's our integration by parts formula. So that's t e to the t minus the integral of e to the t dt. So we've still got our left-hand side intact here. So notice all of the new stuff that we've learned is already done. We already did our first order linear process over here. Now this is all just integration techniques at this point. But we get t e to the t minus e to the t plus c. We need to switch everything back in terms of x now. So we'll go ahead and take advantage of this substitution. So switch everything back from t to x squared. So y e to the x squared equals x squared e to the x squared minus e to the x squared plus c. And now to isolate y, we divide e to the x squared over here. So that's x squared e to the x squared minus e to the x squared plus c all over e to the x squared. And we can go ahead, there's a common factor, split this up across all the different terms. We just get x squared minus 1 plus c over e to the x squared. Now the arbitrary constant, it can absorb any constant. It cannot absorb a function with variables. So it cannot just absorb e to the x squared. That has to stay there. But this would be our final fully simplified version. So this would be the solution, the general solution to this differential equation. So that value, that function y, would solve that differential equation on the left-hand side there. So let's take a look at one more. Bringing some trig into the mix here. Solve y prime equals sine of x times y secant of x minus 2. Now on the face of it, this doesn't already look like a first order linear problem, but we can make it look like one. We can move things around a little bit to put it in the proper form to do that. So distribute the sine of x. Now sine times secant. Remember, secant is 1 over cosine. So you're going to get sine over cosine, which is just tangent. So this becomes y times tangent of x, and then minus 2 sine of x. We're going to move this term over. So y prime minus tangent of x times y equals negative 2 sine of x. And this has the general form of the first order linear. So y prime plus a function of x times y equals some function of x. Okay, so this gives us p of x will be negative tangent of x. Q of x will be negative 2 sine of x. So I, in this case, so I of x, that's e to the integral of negative tangent of x dx. So the negative will stay out there, but the antiderivative of tangent does introduce another negative. So that's negative ln of absolute value of cosine of x. the two negatives cancel, so we have e to the ln of absolute value of cosine of x. E and ln will undo each other because they're inverses, so we're left with the absolute value of cosine of x, but notice the domain. We are on the interval 0 to pi over 2 for x. 0 to pi over 2, cosine is always going to be non-negative on that interval, so we can go ahead and drop the absolute value. So no absolute value because of the domain. But that's our function I of x. So now we set up this equation. So I times y on the left-hand side. So cosine of x times y prime equals I times q. So that's -2 sine of x cosine of x on the right-hand side. If we integrate both sides of this, on the left-hand side, the integral and the derivative will cancel. On the right-hand side, we'll get, so integral of -2 sine of x cosine of x dx. So we can solve this using just like a u substitution. So if you let u be sine of x, du is cosine of x dx, and that covers it sufficiently. So we have cosine of x times y equals negative sine squared of x plus c. And then we just need to isolate the y by dividing by cosine. So we get y equals negative sine squared x plus c all over cosine of x. And that would be our general solution to the differential equation. And there's not really any simplifications there that would necessarily make this better. In terms of like simplifying it down, you can make it look different depending on which trig functions and trig identities you want to use. But this is about as simple as it gets in terms of the final answer. But this would be the solution to that general, so the general solution to that differential equation. Up there, the y prime equals sine of x times y secant x minus 2. So if we were to solve this, right, take its derivative, and then substitute both of those back into this original function, you would see that you get out a true statement. But that brings us to the end of section 1.6 and our introduction to the concept of first-order linear differential equations.